Okay, welcome everyone for Mohammed Mahbub Kabir's candidate assessment stage 3. I'm the panel chair, Yang Chu, and then the supervisor is Professor Ho Kyung-sean, and then the co-supervisors are Professor Zhang-Go Huang, and then the associate professor Lana Tihin. And the assessors are Associate Professor Sharob and then myself. So before we start, Mahbub, when is your thesis submission due?
I have to submit my thesis by 3rd of February
3rd of February.
next
Okay.
year.
Okay. All right. So you have 2 more months. Okay. So yeah, please present your presentation please make sure to finish in 30 minutes.
Are you
30 or
recording?
40 minutes.
Okay.
What did you say, Sharon?
It's
Okay.
30 or 40
Recording.
minutes.
Oh, I started recording. Yeah, 30 minutes, please. It's 30.
Okay. Good afternoon, everyone. This is Mahbub, and welcome to my CA3 presentations. Today, I'm going to talk about the predictive design of anion exchange nanocomposite membranes for water electrolysis. I will talk about the background of my thesis, the research objectives and thesis outlines, some general experimental techniques, and the core experiments, what I did in my PhD thesis. And finally, I will talk about the summary and outlook, some publications and acknowledgements. So our current global energy is fossil fuel dominated. As you can see that the fossil fuel based energy consumption is increasing with time. And Australia is the the second highest per capita energy consumer. However, the fossil fuel reserve are reducing rapidly. In the next decade, it will be almost finished. And the fossil fuel derived energy burning can lead to the increase of greenhouse gases like carbon dioxide, methane, nitrous oxide. And this kind of gases concentrated in the global atmosphere, which increase the global temperature and ultimately causes the global warming problems. So how can we decarbonize the global energy system to achieve the net zero emission by 2050? One way could be include the renewables energy into our existing energy system. And in this case, hydrogen could be one of the most promising one because hydrogen has the high energy density per unit mass, and also hydrogen is one of the most great energy carrier. Let's have a look around in the global hydrogen market in 2025. The global hydrogen market was 282 billion US dollar, which increased to 556 US dollar in 2034. And the global hydrogen will be increased. Global hydrogen demand will be increased to 7 to 8 times compared to, in 2050 compared to the 2022, which constitute 22% of the global energy. And to achieve the net zero emission by 2050, we need 660 million ton of green hydrogen. There are a lot of colors of hydrogen, but we can see only green hydrogen can produce the low emission carbon hydrogen or low carbon hydrogen. And this green hydrogen can be produced by water electrolysis technology. There are several kinds of water electrolysis technologies like alkaline water electrolysis, proton exchange membrane water electrolysis. However, in alkaline water electrolysis used a highly concentrated alkaline feed from 1 to 6 molar kWh, which caused the undesirable side reaction, electrode corrosion, and also the gas crossover in the electrolyzer, which ultimately decreased the hydrogen production efficiency. On the contrary, proton exchange membrane water electrolysis use the precious metal catalyst, especially the transitional metal catalyst, and also they use the commercial Nafion membrane, which is highly expensive materials. But anion exchange membrane water electrolysis is the emerging one, and this technology is the most compact one, and it is a hybrid technology, use the advantage of both proton exchange and alkaline water electrolysis technologies. However, there are several problems in anion exchange membrane water electrolysis, especially in the membranes. The most significant problem is the trade-offs, like trade-offs between the different attributes of the membrane, like electrochemical, dimensional, and mechanical stability. So if we want to develop the mechanical stability, we have to compromise the dimensional or electrochemical stability of the membranes, which ultimately results the fragile in alkaline membrane and also decrease the overall cell performance of the water electrolysis systems. So there are several key innovation areas we can use to eliminate this kind of trade-off, like we can develop the hydrophilic and hydrophobic microfast separation structure within the membranes matrix. We can use the molecular design structure of the polymer. We can make the polymer backbone architecture design. We can use the functionalized nanomaterials to make the percolated ion pathways to eliminate this kind of trade-offs and make the anion exchange membrane water electrolysis highly effective. Machine learning and AI nowadays has been increasingly used in water electrolysis to identify the key trade-offs and set the benchmark of hydrogen ion conductivity to determine the influential performance of different features of the water electrolysis, and also to provide the insight into catalyst design, especially the MEA preparations. There are several machine learning technology, machine learning models popular in the water electrolysis technology. Among them, random forest, catboost, and axiboost. These three models are most popular ones in water electrolysis technology because of their predictive performance. So my thesis adopts a three-stage predictive experimental research strategy. The study begins with a comprehensive machine learning study to identify the existing problem in the anion exchange membrane. Like we got three problems in our machine learning study. Like we identify the key trade-offs, we find out the optimal ion conductivity, and we find out the most influential key process parameters which can affect the hydrogen production or the current density. And then as a direct extension of machine learning analysis prediction, this work then transitioned to experimental validation, where we use the QPPO Maxine system to eliminate this kind of trade-offs. This QPPO Maxine AM system show very promising current density, also the ion conductivity, but this study is limited by, as you can see, this low alkaline stability and the low compatibility with the polymer matrix and the nanomaterials. So to eliminate this kind of problems, and based on the demonstrated gains in QPPO Maxine systems, this study then advanced to an ether-free, highly alkaline resilience polymer, especially the quaternized polycarbazole, and we used the highly dispersible ionic liquid functionalized graphene oxide into the QPPO matrix to eliminate these problems and to achieve the high performance of ion conductivity, cell performance, and alkaline stability. So my thesis structure include the first chapter include the background of my research, and the second chapter include the recent advancements of the anion exchange membrane water electrolysis technologies, and chapter 3 includes some general techniques, and chapter 4 to 6 is my core research area, how I can innovate in water electrolysis technology, and finally I had some summary and conclusion of my thesis. So I fabricated my anion exchange membrane by a very simple solution casting technique. As you can see, this is the fabricated membrane in our study. So we measured the electrochemical stability of the membranes by a simple ion conductivity cell, so with potentiostated by galvanostatic impedance spectroscopy techniques. And our membrane electrode assembly has been prepared by catalyst coated surface substrate techniques with the air gun spray. And we used PTL and GDL as the anode and cathode substrate. This is our anion exchange membrane water electrolysis cells, including the electrode, GDL, PTL, and the anion exchange membrane, and also gasket. This is our water electrolysis cell and alkaline water electrolysis test station, and this is the test condition: cell temperature, cell effective area, electrolyte concentration, and the feed flow rate. And for the long-term duration, we use the 150 hour for QPPO maxine system and 240 hour for QPC ILQ FGO anion exchange membrane system. This is my objective one from this study. I figured out the existing anion exchange membrane water electrolysis problems. So several processes include the methodological framework of machine learning of anion exchange membrane water electrolysis systems. First, we collect the data from both manual extraction and webplot digitizer techniques, and then the data were cleaned and processed. And after that, we select the feature and did the correlation. After correlation, we split the data into training and testing set. And then we developed the machine learning model. During the machine learning model development, we did hyperparameter tuning and careful cross-validation technique, especially careful cross-validation technique to improve the model performance. And finally, we identify the model evaluation techniques by regression coefficient and determining the error values. We also identify the most significant process parameter that could contribute the cell performance of anion exchange membrane water electrolysis by shape, PBI, and PDA techniques. This table shows the key process parameters involved in my machine learning modeling techniques. We used 19 process parameters, including general process parameters, membrane electrode assembly process parameters, and the anion exchange membrane process parameters. We ranked 9 features out of 19 features by recursive feature elimination techniques to develop the models. And multi-phase correlation, like correlation heat map and partial correlation network analysis, showed that the processes or the anion exchange membrane processes have key trade-offs between the electrochemical, dimensional, and mechanical stability of the membrane. Especially, we can see there's the ion conductivity shows a positive correlation with the cell performance. Among the tested 7 models, random forest and catboard showed the highest predictive performance with an R-square value of 0.95 and 0.91 respectively, with a minimal error values. On the contrary, the XGBoost and GBoost showed a very moderate performance or predictive performance of the machine learning models. So this table shows the details of the training set and testing set results. The PBI and shape-based analysis of feature contribution for CatBoost model analysis showed that ion conductivity is the only predictive contributor that can significantly contribute the model performance as well as increase the hydrogen production rate. So the partial dependency analysis for CatBoost model, both one-way and two-way variables, indicated that anode catalyst loading up to 2 milligram per centimeter was considered optimal, and the ion conductivity up to 250 millisiemens. Ion conductivity up to 250 millisiemens per centimeter should be threshold for the high performance water electrolysis, and also the cell voltage up to 2 volts should be optimal for anion exchange membrane water electrolysis system. The partial dependency analysis for random forest model showed a similar trend for the random forest model, as like CatBoost model. So in conclusions of this chapter, we can see there's the multi-phase correlation, identify the notable trade-offs, and PBI and shape techniques identify that ion conductivity is the most significant predictor of current density or hydrogen production. And partial dependency analysis suggested that an ion conductivity of 250 millisiemens per centimeter should be threshold for the hydrogen production rate in an anion membrane water electrolysis system. And also we find a limitations because our data says what was limited. Only our data sets consist of 410 data sets. So it could be a limit certain aspects of statistical inference of the modeling. As a direct extension of machine learning predictive analysis, so this QPPO mixin study transition to the experimental validation, where we try to eliminate the key trade-offs that we found in the our machine learning modeling techniques. The brominated polyphenol oxide and quaternized polyphenol oxide developed by bromination and quaternization techniques. However, on the other end, the mixin materials, especially the ammonium functionalized mixin, was developed by etching with the ammonium dihydrogen fluoride. And the mixin and the nanomaterials and polymers interacted with by interfacial hydrogen bond or a electrostatic bonding techniques. We characterize the mixin by XPS, FTIR, XRD, and HRTM techniques. On the other hand, we characterize the polymer by 1H NMR and FTIR techniques. Here you can see this our thickness of the membranes, especially the QPPO mixin membrane, varied from 40 to 15 micrometer. The membranes are densely smooth and devoid of significant agglomeration or defects. We can find the control water uptake and sealing ratio ranging from 17.8 to 36.2% and 6.5 to 16.2% respectively. And the optima membrane demonstrated an IEC of 2.52 millimole per gram. On the other hand, the tensile strength of the anion membrane ranged from 15.2 to 61.2 megapascal. As you can see, this the AFM micrographs of pristine QPPO membrane and the optimized QPPO NH4 308% membranes. There is a distinct hydrophilic and hydrophobic domains as confirmed by the Sachs analysis, where we get the d-spacing ranging from 1.78 to 4.27 nanometers. So combinedly, the AFM and Sachs analysis suggested that these membranes developed a very well connected microphase separation structures, which ultimately leads to an impressive ion conductivity of 153.2 millisiemens per centimeter. We also showed some comparative study with the ion conductivity and sealing ratio with the membrane in the literature and also some commercial membrane, and we found that this study is almost comparable and outperforms some of the membranes. The alkaline stability of the optima membrane was 80.2%, and the membrane also shows the excellent thermal stability. And the single cell performance of this QPPO mixin AM system showed an current density of 2.1 ampere per centimeter square at 2 volt. And in the long-term water electrolysis up to 240 hours, we also see the stable performance with a minimum voltage decay rate. So this is the overall working mechanism of our QPPO mixin system. Here we can see that the QPPO mixin hydrophilic structure and hydrophilic functional properties, and also the hydrophobic polymer create a percolated ion pathways that can increase the ion conductivity, and the hydrophobic phase of the polymer can reduce the sealing and the mechanical stability of the membrane. We also performed the comparative study of our QPPO mixing system with the commercial membranes, and except the Papillon one, we can see this our cell performance is almost comparable with the commercial membrane. However, we found that the long-term duration study of our membrane is somehow limited in the QPPO mixing system. So in conclusion of this chapter, we eliminated the key trade-offs like mechanical, electrochemical, and dimensional properties of the membrane. And the optimized membrane demonstrated a very impressive ion conductivity and a very excellent tensile strength of 61.2 megapascal, which is 4 times compared to the pristine quaternized polyphenol oxide. We also achieved an impressive current density of 2.1 ampere per centimeter square. And also the alkaline stability, we found 80.2% of its initial ion conductivity retaining. However, this study showed some limitations, like the nanofiller dispersion was not good. It showed some agglomeration in the SEM, and also alkaline stability needs to be improved, and the durability study should also be extended. And our machine learning study, we found that ion conductivity and the cell performance also need to be improved in this study. So to eliminate this limitation, my thesis advanced to an ether-free alkaline resilience polymer like quaternized polyphenol oxide. We synthesized the ionic liquid by a simple quaternization technique, and ionic liquid functionalized graphene oxide was synthesized via a covalent grafting. On the contrary, the brominated polycarbazole was synthesized by acid-catalyzed electrophilic condensation polymerization reaction, and the brominated polycarbazole was quaternized by TMA solution to synthesize the quaternized polycarbazole. Here you can see the characterization techniques of ionic liquid. We characterize it by 1H NMR, FTIR, and TGA techniques, and it shows the successful synthesis of imidazolium-based ionic liquid. We also characterize our ionic liquid functionalized graphene oxide by XRD, FTIR, and XPS techniques. The polymer characterization was done by 1H NMR and FTIR, which provide the successful conformation of polymer materials. The thickness of this membrane varied from the similar QPPO mixing system, 40 to 50 micrometer. However, in this case, you can see that the same image, the membrane is smooth, very smooth, defect-free surface with no microvoids or pullouts. And the optimized membrane shows a water swelling ratio of 26.21%. On the contrary, a water uptake of 41.4% at 80 degrees Celsius. The ISA value ranged from 2.1 to 3.2 at 3.01 millimole per gram at 100% loading of ionic liquid functionalized graphene oxide. Also, we find that the incorporation of ionic liquid functionalized graphene oxide can increase the tensile strength of the membrane up to 55.55 megapascal. The AFM micrographs of quaternized polycarbazole-based membranes also showed the distinct hydrophobic and hydrophilic regions, and which is also confirmed by the SAX analysis. So the SAX analysis shows a despacing range of 2.6 to 3.21. So we also can see that this QPC ILQ-FGO system also developed a very well-developed microfast separation structures with a tortuous percolated ion pathways, which leads to the ion exchange ion conductivity of our QPC ILQ-FGO system up to 280 millisiemens per centimeter, which is almost double compared to the pristine QPC membrane. So we also try to compare the ion conductivity versus IEC water uptake and sealing ratio with the commercial membrane or some of the literature driven membranes, which also see that our membrane is almost comparable, and sometimes it outperforms from some of the membrane in the literature. We also can see that the single cell performance of QPC optimized membrane recorded a peak current density of 4.61 ampere per centimeter square. And the long-term stability up to 240 hours of water electrolysis showed a minimal voltage decay rate of 0.3 millivolt per hour. And the alkaline stability in this case increased to 92% for the optimized membranes, which is almost similar to the quaternized polycarbazole membrane, because QPC is itself is a highly alkaline resistance. So from these findings, we hypothesize that the QPC ILQ-FGO membranes demonstrated dual ion channels to improve the properties. So the most probably the primary pathway of ion transport occurs along the ionic liquid functionalized nanosheets, where the cationic imidazolium sites form a percolated low resistant channels which enable the first ultra fast hydroxide transport. And the second pathway is through the intrinsic polymeric channels of the quaternized polycarbazole backbone, which provides stable continuous ionic conduction across the bulk solution. We also see the membrane hydrophobic phase can ensure the mechanical stability and the dimensional stability of the our QPC ILQ-FGO membrane. And also we have to note that this ionic liquid is highly dispersible and also very conductive materials. We also recorded the cell performance of cell performance and ion conductivity of polycarbazole-based membrane historical data. As you can see, from 2090 to 2025, we recorded the cell performance, and from except this one, all of the our membranes outperforms all of the literature membranes recorded in the past. In terms of ion conductivity, we found a very highly recorded or remarkable ion conductivity up to 280 millisiemens per centimeter, which outperform all of the recorded anion exchange membrane in the literature. We also compare our quaternized polycarbazole ionic liquid functionalized 1.58% membrane with the commercial and literature membrane. So if you can see that in terms of dimensional stability, mechanical stability, electrochemical stability, and single cell performance, also the long-term durability. So our membrane, the optimized membrane, showed a very competitive performance, and in terms of cell performance and other performance. The only limitation is we do a long-term durability only 240 hours of electrolysis. However, in the literature, the commercial sustained membrane, they do a durability analysis of 1,000 hours. So in conclusion of this study, we can find out that the membrane showed a balanced performance of dimensional, mechanical, and electrochemical stability with an impressive ion conductivity of 280 millisiemens per centimeter, and also a peak current density of 4.61 ampere per centimeter square at 2 volt. We also found that excellent alkaline stability of 92% at 1 molar QH after 3 weeks immersion in 1 molar QH. The membrane also showed the stable water electrolysis operation with a minimal voltage decay rate of 0.35 millivolt per hour up to 240 hours of water electrolysis. So from this study, we can find that the two limitations, like for the large scale fabrication of the membrane, the refining of process conditions, and also the surface engineering of ionic liquid functionalized graphene oxide is further remaining to improve the both cell performance and the ion conductivity of the QPCI-LQFGO system. Also, we can see that the higher loading of ionic liquid functionalized graphene oxide can decrease the mechanical strength, especially the elongation and break to some extent. So the further study, we can develop some kind of cross ether free, ether containing flexible cross-linker or different spacer like SCBS to improve the mechanical strength of the membrane and the flexibility of the membrane. So my final conclusion of my thesis included we established a predictive experimental framework for anion exchange membrane water electrolysis. The ML prediction identify the key trade-offs and the ion conductivity threshold of 250 millisiemens per centimeter. The experimental validation through QPPO mixing and QPCI-LQFGO system successfully translated into ML insight into materials with exceptional conductivity, durability, and dimensional stability. The QPPO mixing AM achieved a high mechanical strength and improved stability, while the ionic liquid functionalized graphene oxide QPC system delivered a remarkable hydroxide ion conductivity, also the cell performance and long-term durability. Collectively, we can say that my PhD thesis work bridges the data-driven prediction and molecular level design, offering a scalable pathway toward durable, efficient, and economically viable anion exchange membrane water electrolysis system. The future research work should be focused on expanding the AM dataset and predictive feature space to enhance the machine learning model robustness and applicability. We can scale up the fabrication process and explore advanced surface engineering of the nanomaterials to translate the lab scale membranes into commercial anion exchange membrane water electrolysis stacks. Also, if we want to commercialize these membranes, we need to extend the durability and alkaline aging up to 1,000 hours. So far in my PhD study, I have published 25 papers. Among them, I was first author in 15 papers, and this 14 papers is directly relevant to my PhD study. And this 11 paper is from collaboration with my supervisor, co-supervisors, and some of my other collaborators. I have also attended 4 national and international conferences. And finally, I would like to acknowledge my supervisor, principal supervisor, Professor Ho Kyung Shon, and my co-supervisor, Professor Jinggu Huang, and Associate Professor Leonard Thijing. I would like to thank my panel chair, Dr. Yango Chu, and my assessor, Professor Sherub Funcho and Dr. Yango Chu. I would like to acknowledge my funding agency, Australian Research Council Industrial Transformation Research Hub on Nutrients in a Circular Economy, And I would like to also acknowledge the funding support through the UTS President Scholarship and International Research Scholarship throughout my PhD study. I also would like to acknowledge my peers and my friends, Yeshi, Mosen, Dai, and Junkai during my PhD candidature. Thanks, everyone. I hope, thanks for